Good afternoon. My name is Sylvia Schwag-Serger. I'm a professor of research policy and currently president of the Royal Swedish Academy of Engineering Sciences. And it is my honor and pleasure to welcome you to this seminar this afternoon on sustainable magnets, on magnets for a sustainable world. Sweden and Japan have a very long-standing history of scientific research and innovation collaboration. And I have witnessed this collaboration myself. I spent 10 years at the Swedish Government Agency for Innovation, Vinnova, where I was in charge of international collaboration. And I've also been chair of the board of the Swedish Foundation of International Collaboration in Research and Higher Education, STINT. So what I have witnessed is long-standing scientific collaboration between Japan and Sweden, one of the most long-standing relations we have, but also a very mutually, I think, appreciated relationship between partners that can rely on each other, that trust each other, and that share a lot of common values and interests. And this kind of trust-based collaboration around common interests and around a shared belief in science, the value of science, but also the value of innovation, and, for example, more recently, the joint interest in addressing societal challenges, for example, through the Sustainable Development Goals, is, I think, a partnership and a collaboration that is particularly important in these times of geopolitical turbulence. So this even more enhances the value of the collaboration, the long-standing collaboration between Japan and Sweden. And the collaboration, I believe, is very strong also because it combines bottom-up collaboration between outstanding scientists with some government-driven initiatives and institutional arrangements to further strengthen the collaboration. So I know at Vinnova we collaborated for many years with JST, on research and innovation partnerships. I know that the SSF, the Swedish Strategic Foundation, has for a long time collaborated with JSPS. I also would like to mention the Mirai initiative, which was created by STINT, which I think is unique in its kind, in that it brings together the majority of universities in Japan and Sweden in an institutional collaboration, which I believe is unique, at least on the Swedish side, and provides a very important institutional embedding for this flourishing collaboration. At the government level, EVA is the organization which first created the function of technical attachés in the 1960s, and Japan was one of the first countries where EVA stationed a technical attaché. And on the Japanese side, we also know that Sweden is one of the countries where Japan has science fellows, and it's not that many other countries in the world where Japan has science fellows. So I think that all these things that I'm telling you sort of underline, but also serve to reinforce this incredibly valuable, mutually beneficial collaboration, which I think and hope also just not only benefits Japan and Sweden, but science more generally. Furthermore, we have a collaboration which spans many sectors, so not only academia, but also large industrial companies working on innovation collaboration together, and a collaboration around large research infrastructures. So another initiative among the many that I've mentioned is that one run by the Sweden-Japan Foundation, which supports visits to Japan for studies, research, or internships. And for over a decade, the Academy has regularly collaborated with the Sweden-Japan Foundation, with the Japan Society for the Promotion of Science, JSPS, and the Japanese Embassy in Sweden to organize top scientists' lectures such as this one today. This year, the event is also supported by the Swedish Foundation for Strategic Research, which we are very happy about. I want to thank each of you, as well as the EVA fellows, and I also forgot to mention that I think Japan is one of the countries from which we have the largest number of international fellows at EVA, which we're also very proud of. So I want to thank you all for initiating the specific topic of groundbreaking advancements in magnetics and their impact on society. With this, I want to wish you an interesting and a successful seminar, and I thank you all for your support in this collaboration and in bringing it into the future. Thank you very much. I will also hand over to Eva.
Thank you, Sylvia. Your Excellency, ladies and gentlemen, it's a fantastic 2 hours we have in front of us in the field of magnetics. That will be really cool. You can see the program, I think, on the next slide. I will show you that one. And we have a few speakers here. We picked them very thoroughly. These are the highest level there is on this planet, ladies and gentlemen. I hope you will appreciate this today. I'm Eva Krutmeier. I'm a science communicator, and as Sylvia also said, I'm interested in collaboration, and I sometimes call it bridges, like bridges from basic science to innovation, from innovation to business, from business to society, from society back to basic science, you know? So this is a whole fantastic system, and we all play a role in it. Before we welcome the first speaker, a legend in the field of permanent magnets, Dr. Sagawa, I think it therefore can be helpful for us to place his work in a wider context. To help me with this, I would like to welcome up our second speaker, Dr. Nora Dempsey. So please, Nora, come up and give her a hand. So, I'm so glad that you helped me with this, because it's quite technical. It is quite hard. What are these permanent magnets, really? If you would tell a dummy, sort of, what are they for, and what are they used in, you know?
Okay.
Because this is really, we've learned it's an emergent technology, but for what?
Okay, so permanent magnets, they're essentially a piece of magnetic material, and once you've magnetized it, it's going to remain magnetized. So it is a magnetic field source which has no running costs. So this is very important.
Forever and ever.
Forever and ever, at least if it's a good one, like what Dr. Sagawa made. Then what do we use them for? A first example, we can consider interactions between permanent magnets and other materials, and so we can use them to push or pull materials. A good example is your fridge magnet, okay? So your fridge magnet will stick on the fridge because it's attracted to the iron or some other ferromagnetic material in the door. Then we can go further. We can consider interactions between a permanent magnet and a coil. And here, this is extremely important for the whole field of electromechanical systems. So we can either consider converting mechanical energy into electrical energy. So this is what we do in people who are old enough to remember dynamos of bicycles or in a windmill. But inversely, we can actually use magnets and magnets combined with coils to go from electrical energy to mechanical energy. So first good example is a motor. Think of your washing machine. A second example would be for actuators. So think of a loudspeaker.
We can't even think of the society without magnets.
No, no. And I will talk a lot more about
you will, but
about
you know
applications.
What? Now, even in the Oval Office, they speak now about the rare earth metals.
Yes.
So what on earth are they doing in the permanent magnets? What is the connection there?
So let me first say that a permanent magnet, the defining characteristic of a permanent magnet is its coercivity, because this is what quantifies its resistance to being demagnetized. And there are two ways to induce coercivity. So the first is simply using shape anisotropy. So if you can think back to, say, the iron needles used in a compass or horseshoe magnets, these depended on shape anisotropy, okay? So think of an iron needle. If everything is pointed, if the moments are pointed along the bar of the needle, you have a few poles which are very far away. That's okay. If you try and magnetize it this way, you have a lot of magnetic poles which are close together, and nature doesn't like this. So this is why you're going to have. This is why it's much better to have a bar magnet, and then you can actually take a bar magnet and you can fold it to make it more compact, and then you can even get a little bit more stray field between the poles. But these are old magnets which are...
So the rare earths, what are they doing there?
So they don't exist there. Now we're going to think about the second method for getting coercivity, and this is much, much more powerful, and this is based on magnetocrystalline anisotropy. And now, without going into details, just what's important with rare earth elements is that they have these very anisotropic shape of the charge cloud in the 4f electrons, if you know what they are. So basically you have an anisotropic distribution of charged cloud. Then if you manage to if you take a rare earth and put it with a ferromagnetic atom like iron or cobalt, and if they make a compound which is anisotropic, then it's possible to actually induce a very favored, like a uniaxial direction. And this is what's giving you the coercivity. So it's really the very particular electronic structure of rare earths which is crucial to permanent magnets.
Thank you so much for clarifying this, because I think we need to have this in our back head when we listen to also your speak today, but especially Dr. Sagawa. So thank you so much, and welcome back soon.
Okay, thank you.
We always have use for an Irish physicist, don't we? So it's now my privilege and honor to hand over the scene to Dr. Masato Sagawa. This is the inventor of the sintered neodymium iron boron permanent magnet. This is the strongest permanent magnet there is in the world. We've just heard from Nora how it has revolutionized the world of magnets and positively also impact our society, from electronics to electrical motors and renewable energy. So, in the early 1980s, the strongest permanent magnets were actually made from a combination of samarium, if I'm correctly understood here, and cobalt. Materials that were both expensive and scarce. Recognizing the need for a more cost-effective solution, Dr. Sagawa experimented with iron and various rare earth elements. His breakthrough, and he will tell us more about this, came when he introduced boron into a neodymium and iron alloy, resulting in a magnet with unparalleled strength and resistance to demagnetization. This is a hard word. So please give a warm hand to Dr. Masato Sagawa from Daido Steel Company in Japan. Welcome. You can use the clicker here.
Yes.
There we have that one, and everything is prepared.
Okay, thank you very much for the introduction. And I'm very glad to be here. And I prepared this talk, development of permanent magnet production, development of production technology for neodymium iron boron sintered magnets. Hi, I belong to Daido Steel, but before let me introduce. I am Tohoku University alumnus and distinguished invited university professor of Tohoku University. Very, very honored. Okay. I have always wanted to be a scientist since I was a child, but I never succeeded. However, my passion for research paid off, and I became the inventor of the world's strongest magnet. I am happy to be able to tell you the story of how I got here. Since everyone here today is from the engineering sciences, I understand. So I will now talk about the manufacturing process of neodymium iron boron magnets and the problems they face. I hope that we can work together in this field. Okay, this is the first paper on the neodymium iron boron sintered magnet. The title is New Material for Permanent Magnets on a base of neodymium and iron. This is a first paper. And I was working for Sumitomo Special Metals, as you see. And oral presentation of the paper was made at MMM conference on November 10, 1983. The person next to me is a chairperson, Professor Carl Strunat, who discovered samarium cobalt-5 magnets. Okay, in this paper, I presented that we found a new tetragonal compound for permanent magnets. Tetragonal crystal structure with lattice parameters. A is 0.880 nanometers, and C is 1.221 nanometers. And we determined the single phase region as 12 atomic percent neodymium, 6 atomic percent boron, and iron for this compound. And these figures show compositional dependence of magnetic properties. On the left, neodymium content dependence, and on the right, boron content dependence. And this composition, 15% neodymium and 8% boron, this composition is determined as the core of the new products in Sumitomo Special Metals, named Neomax. And SEM image of the neodymium iron boron sintered magnet, it proved that the microstructure is ideal for the nucleation type magnets. This shows that changes in magnetization and demagnetization curves of this neodymium 15 boron 8 iron 77 magnet due to magnetizing field. And fully magnetized BH maximum shows 290 kilojoule per cubic meter. This is a new world record of the energy product. And this shows the evolution of the world's strongest permanent magnets. When it appeared in 1982, the BH maximum was 290 kilojoule per cubic meter. And after that, this record, world record, was improved many times to reach the upper limit of the neodymium iron boron, which is 480 kilojoule per cubic meter. And this is my laboratory and the team at SSM. The team was over 20 people, and I am very proud of this team. In 1985, my research team established the framework of the mass production process: melting, crushing, jet milling, pressing in magnetic field, and sintering and annealing. This shows the global production of neodymium iron boron sintered magnets. SSM, Sumitomo Special Metals, started the mass production of the neodymium iron boron sintered magnets only 3 years after the invention. In 1985, the production quantity was 100 tons per year, and next year 200 tons, and 1988 it reaches to more than 400 tons. I resigned from SSM in 1988 and set up my own company to perfect the sintered neodymium iron boron magnet while maintaining good relations with Sumitomo Special Metals. To perfect the sintered neodymium boron magnets as magnets for a sustainable world, there are three subjects. Number one, heat resistance. Heavy layers-free magnet with BH maximum is 50 megagauss Elsted or higher. Number two, near net shape manufacturing process. Number three, low eddy current loss magnets with BH maximum is 50 megagauss Elsted or higher. Okay, the first subject, heat resistance, heavy layers-free magnet with BH maximum 50 megagauss Elsted or higher. Why is heavy layers-free needed? This is because neodymium iron boron sintered magnets produced from 5-micron powder is heat resistance only to 100 degrees Celsius. For motor applications such as EV motor, heat resistance to 200 Celsius is required. Heavy layers addition increases coercivity of the magnet to improve the temperature stability, but dysprosium, terbium, or heavy layers, typical heavy layers, dysprosium, terbium, are both less abundant as resources. A method must be found to increase coercivity without heavy layers. So this subject, how to deal with the problem? A way to increase coercivity without heavy layers is to refine the particle size of the powder. Okay, this shows a relationship between coercivity and D50 for neodymium iron boron magnet without dysprosium. D50 means average particle size of the powder before sintering. And as you see, the coercivity without the particle starting point is this black star, 5 microns. And at this time, the coercivity is 13 kilodestet, and we expect the coercivity increases along this line to reach this yellow star. This is a goal, 25 kilodestet at 0.9 micron powder, our target for heavy layers-free magnets. Okay, so experimental results is as follows. Coercivity starting point is 13 kilodestet at 5 microns, and by decreasing to the particle size to 3 microns, the coercivity increased to 15.5 kilodestet. But by using nitrogen jet mill, and to decrease 1.2 micron powder particle size, the coercivity reached to 20 kilodestet. But to get 1.2 micron powder, helium gas jet mill has to be used. Helium. Why helium? Mechanism of helium gas jet milling. By using helium gas jet, the raw material coarse powder can be collided with the target at high speed, resulting in a fine powder. The helium gas jet can be increased to 1,005 meters per second, 3 times faster than that of nitrogen jet. So by using helium gas, the fine powder is produced. So this is a jet mill plant with helium gas circulation system. Helium gas jet mill is powerful, but we are concerned about helium gas resources and availability. Okay, so how about using H2, hydrogen gas, to produce the neodymium iron boron powders finer than 1 microns? H2 gas jet could be 4 times faster than the N2 gas jet. Moreover, H2 hydrogen is abundant on Earth. So H2 gas jet can be accelerated to 1,308 meters per second, 4 times faster than the nitrogen jet. So it's very powerful. But we have a concern. It would be dangerous to operate the H2 jet mill in air. What about the idea of placing the H2 jet mill inside a glove box filled with nitrogen? So we tested. This is a schematic diagram of the H2 jet mill installed inside a nitrogen gas jet glove box. And we tested H2 jet mill operation here at the Hydrogen Energy Test and Research Center located in Fukuoka, Japan, for 3 days. It was perfectly safe, and we felt H2 jet mill promising. And with the H2 jet mill, we may be able to reach 25 kiloelectrons at 0.9 micron particle size, our goal. We can go to the goal. H2 gas jet mill installed in an N2 chamber may achieve the objective one. But mass production of sintered neodymium boron magnets using H2 gas jet mill may look too risky. I would like to cooperate with European companies of advanced fine grinding technology to industrialize the technology to grind neodymium boron alloys down to 1 micron in argon or nitrogen gas safely. Okay, next subject, near net shape manufacturing process. Okay, all powder metallurgy products have aimed at near net shape manufacturing, but there exists no near net shape manufacturing process for neodymium iron boron sintered magnets. We developed a technology to produce many thin magnets at once directly. This is a process we developed, near net shape manufacturing process for the neodymium iron boron sintered magnet. So this is a mold. Okay. A mold, and okay, this, and it has many cavities separated by thin plates, and powder is filled in the mold. The filling density of the powder is 3.5 gram per cubic centimeter. And then making alignment by applying pulsed magnetic field, and the magnetic powder is aligned. And then the mold is removed, and the stack of compacts is introduced into sintering furnace. And after that, after sintering, you have thin plate magnets directly at the same time, many thin magnets. Okay, this shows the various examples of mold and sintered bodies in near net shape manufacturing process. 3 millimeter thick plate. Okay, 3 millimeter thick plate arc segment and 1.45 thick thin plate. We had a very good magnet. with various shapes and thickness. So, we made a evaluation test of the near-net shape manufacturing process technology by producing test samples. How about the result? We aim for dimensional and magnetic properties variation to be within 1%. Variation should be very small to use motors for to use the magnets for motors. So this is a powder, chemical composition and particle size distribution of the jet milled powder to produce test samples. Composition, it does not contain heavy layers, only neodymium and praseodymium, and OCN concentration. Contamination level is enough low, and the particle size distribution very sharp, and average particle size is almost 3 microns. And this shows mold used in the evaluation and sintered bodies made from the mold. Mold has 15 cavities, and the powder is filled in each cavity at the average filling density of 3.5 grams per cubic centimeter. And we had 15 sintered bodies. After sintering, the density reaches to almost full density, 7.52 grams per cubic centimeter. And we made a dimensional variation test, and we measured variations in length A and length B, the height, and thickness T of sintered bodies. Variation in A, width variation. Our goal is the variation is 1%, but the variation in A, 1.25%, a little bit higher than our goal. And about B, the height, the variation was 1.41%. It's also higher than our goal. And the thickness variation is large, 3.83%. So it's difficult to reach to 1% the goal. And how about magnetic properties variation? We cut out 6 cubes from each sintered body, and this shows the variation in BR, the BR radiation, the magnetization variation is 2.15%. It's higher than 1%. And how about coercivity? Coercivity variation is also 4.2% high. So we were not able to reach the goal. So near-net shape manufacturing process technology development status before 2023. The near-net shape manufacturing process developed had large dimensional and magnetic property variations, and the situation as of 2023 was that the variation target of 1% or less had not been achieved. But we had a great breakthrough. Recently, we made a tremendous breakthrough in the development of near-net shape manufacturing process technology. We plan to put this technology into practical use by the end of the year 2025. Okay. Next subject. Low eddy current loss magnet with BH maximum is 50 MHz or higher. Low eddy current loss magnet means laminated magnet. To decrease the eddy current loss, we produce the laminated magnets. And this research was funded by the Ministry of Environment, Japan. And the title of the research was Development of Low-Cost and High-Efficiency Neodymium-ion boron Laminated Magnets for EV and FCV traction motors. And this is a production process for laminated magnets by near-net shape manufacturing process. In this process, the powder is produced by the ordinary way, and then the powder is filled in the mold and aligned, and mold is removed and sintering. This is a near-net shape manufacturing process I explained now. And by this process, the sinters simplate are produced by this process, and then the sintered simplate are stacked, and then the stack of sintered simplate are hot pressed at around 800 degrees C to produce laminated magnets. And after annealing, the laminated magnet with good magnetic properties are produced. And this shows the structure of laminated neodymium boron sintered magnet. The element magnet, which contains no heavy layers, the thickness of which is 2 millimeters. And terbium F3 fluoride powder insulation layer is sandwiched. A small amount of terbium F3 powder is sandwiched between the element magnet and then hot pressed at 800 degrees C. And the terbium F3 insulation layer, the thickness of which is 10 microns, and the roles of this layer is, of course, it's insulation, and second role is enhancement coercivity by the grain boundary diffusion effect. So this is a laminated neodymium boron sintered magnet samples insulation layer with terbium F3. So by applying hot press, the mechanical strength is high enough, no problem of handling by robot or so. And this is a hysteresis curve of the laminated magnet measured on the full body samples of the laminated magnet using VSM, vibrating sample magnetometer with a superconducting coil by Tamagawa Company Limited. As you see, this has a very high magnetic properties, high BR, high coercivity, and high squareness, very, very good squareness. And this is a comparison of the magnetic properties between the developed laminated magnet and the commercial grade. Commercial grade, X50, X40BH, X32EH, they are commercial grade. So compared to this, the magnetic property is very high. And it has very high squareness. This is also important for the good magnet. So this is a summary for the laminated magnet. Number one, high magnetic properties. It's very high BH maximum, coercivity, and high squareness. And it has heavy layers content is only very small, 0.5 weight%. And low cost, low eddy current loss, almost zero, and no slicing or grinding. So during all process, no slicing, grinding. This is very, very good for the productivity. And laminated neodymium boron magnet do not require machining throughout the process. So preliminary test using the developed laminated magnets installed in the main motor for an EV confirmed that the temperature rise of the motor during its operation was reduced by 35 degrees C. This is very important. Okay, without the lamination, the temperature rises to 200 degrees. But by using this laminated magnet, the temperature reduced to 165 degrees C. This means this is very important. And secondly, the laminated magnets produced using SPS. SPS is a spark plasma sintering, very efficient hot pressing. So hot pressing, very efficient, is cheaper and have better magnetic properties than the conventional laminated magnet. There are laminated magnet using adhesives, but our magnet is produced by SPS is much better. So I sincerely hope that the new sintered neodymium magnet technologies that I have explained today will be utilized in Europe and be of benefit to European magnet manufacturers. I will spare no effort to make this a reality. Thank you for your attention.
Thank you so much, Dr. Sagawa. It was fantastic to follow each step of your journey. Oh. And sometimes when we see it from hindsight, it looks like a straight line, you know. But was it always easy for you? Or was there a time when you hesitated and felt, oh no, I have to give this up?
So,
Did you ever have this sort of down period in your career? What, did you ever think that I will not be able to do this? It's too complicated. He will get help with the... No. Okay. So you knew all the time that you were able to do it?
Yeah.
I have another question for you. Since we are now hearing about the rare earths, you know, in news every day and so on, and we know that you've been dedicated to research and innovation all your life. We heard also that you dreamt about being a scientist, but you
yes,
you became an inventor.
But,
so
that's difficult.
Exactly, but if there are politicians now, maybe even not in Sweden, but in other countries, listening to you and how important it is with innovation. But what would you like to say to them today, given this sort of uncertain and sensitive geopolitical situation?
Yes.
Yes, you prepared an answer for that one.
I prepared the answer. The guiding principle of scientists is to consider the happiness of all humanity. This is nothing to do with geopolitics. For this happiness of humanity, scientists devote themselves to the quest for the truth and are single-minded in developing things that will be useful to society. If a scientist publicly lies, he or she can no longer be a scientist. I hope that politicians around the world will adopt this guiding principle of scientists.
Keep to the truth.
Yes.
Yeah. We can all give a hand to that, can't we? Thank you. Can I also ask you the third question, please? Can we take the third question?
Yes.
Because I thought it was interesting. What was sort of the most rewarding thing that came to your mind working with these fundamental scientific challenges, and if it was that, or if it was the application side to fit the market needs? Where did you find the most rewarding in your case?
Okay, I feel that addressing fundamental scientific questions and adapting inventions to meet market needs are equally rewarding for me. And I encourage young people to take on the challenge of research that addresses fundamental scientific questions.
Thank you very much. And now we will soon, before the end of this year, you will actually present an even better magnet, you told us. So we wish you good luck.
Thank you.
And thank you for coming to Stockholm. Thank you so much, Dr. Masato Sagawa. We have already met Dr. Nora Dempsey. Please come up. Originally from Ireland, now you're professor at the Centre National de la Recherche Scientifique. My French is poor.
It's as good as mine. No.
You've been carried out so much pioneering work on the development of those magnets and opening the route for their integration into diverse types of applications. So this is what we will hear about now. You're both focused on improving the performance of the rare earth-based hard magnetic materials, but also we will learn about the exciting applications of those new magnetic materials. And I've especially asked Nora to tell us a little also about the recycling processes and so on. Maybe we have a minute or two when you're finished. We can talk about that.
Okay.
Welcome.
Thank you very much. So it's my great pleasure to talk about the societal impact of the discovery of neodymium iron boron by Dr. Sagawa. So I'm just going to begin by just flashing up this. So in Dr. Sagawa's talk, you saw these slides where he was comparing, he was showing how there was an exponential growth in the energy product. So just to take a step back, what's important is the energy product. It's something which depends on the coercivity, which I already described. It also depends on the magnetization of the magnet. And in fact, it's a key parameter for comparing magnets because the energy product, it's proportional to the magnetic energy you can store in the magnet and therefore the work you can do with the magnet. And the bottom line is the higher the energy product, then the smaller and the lighter the magnet you need to do a given job. And what we can see here is that neodymium iron boron is by far the most highest performing magnet that exists. So if we, and it's really no exaggeration to say that the discovery of these magnets really revolutionized the design rules for engineers who wanted to make motors, generators, actuators, or whatever using these magnets. Now, if we look again at the energy product, as I mentioned, the steel magnets which use shape anisotropy, they're obsolete now. But all these other magnets are still being used. You use ferrites if you don't need a high energy density. You'll use them because they're cheap. Alnicos, these are magnets which they're extremely stable with temperature. So if you have applications where the stability of your field is important, you're going to use alnicos. Like for example, you don't want the price of your water to depend on the temperature of the day. Samarium cobalt magnets, the very first rare earth magnets, they can be operated at much higher temperatures because they have higher Curie temperatures. So they're typically used in applications in military or space. Now, neodymium iron boron, I'm going to come back to the applications of neodymium iron boron, but I just want to wrap up this slide with showing you the market share. So what's really important to realize is that neodymium iron boron covers about almost two-thirds of the market share if you're thinking dollars. If you're thinking tonnage or weight, then actually the ferrites are more significant. But really the dominance of neodymium iron boron is represented in this graph. So now I'm going to talk about the applications and how Dr. Sagawa's discovery really impacted society today. So I'll begin with the digital society. So the first mass application of neodymium iron boron magnets was in the voice coil motors of hard disk drive. So essentially this is where your data is being stored, and here you have two neodymium iron boron magnets which are in this voice coil motor which is simply serving to scan the read-write head across the disk. And it's because they have high energy products, so you can have very thin flat magnets. This is very important for making compact hard disk drives. And so the excellent quality of the magnets allowed to make smaller and smaller hard disk drives. So this was important for developing small mobile laptop computers, even though a lot of the high-end computers today use solid-state drives. But nevertheless, neodymium iron boron opened the way for laptop computers, where hard disk drives are really still important today. They are really the backbone of energy data storage centers, because this is where the non-volatile memory is stored. We can also mention smartphones, because I think everyone here has a smartphone, and you have loads of little neodymium iron boron magnets serving different purposes. So again, this is related to the digital society, because most people use their smartphones to access. So already in this room, we know that there are thousands of neodymium iron boron magnets. If we go to another area which is extremely important, so the whole green energy transition. So I'll begin with saying a few words about electron mobility. And so Toyota were the first company to use neodymium iron boron magnets in their hybrid electric vehicles. So the magnets were used both in the powertrain for the motors to actually make the magnets move, the cars move. They are also used in the generators, which are used to recover energy, say when you're braking car. So first was in hybrid electric vehicles, but now you can find neodymium iron boron magnets in all type of electric vehicles and even fuel cell vehicles. Just while we're talking about magnets, so it's not directly related to the green energy transition, but it's very interesting to note that there are over 100 neodymium iron boron magnets used in cars, be it for safety or comfort features. And then coming back to e-mobility, again, the very high energy density is crucial for the emergence of electric bicycles and scooters, which can really benefit from the high magnetic energy stored in neodymium iron boron magnets. So staying with the green energy transition, but now thinking about wind power. So thanks to the energy density of neodymium iron boron magnets, we saw the evolution of geared windmills towards gearless windmills. And so what's very important with having a gearless or direct drive windmills, you have a lot less mechanical parts, so you have a lot less risk of breakdown, so they're much more reliable. And as a result, a lot less maintenance required. So this is very important if you're putting the magnets offshore. And as well, because there are less mechanical parts, you have much higher energy efficiency for power conversion. Yep. Another very important area is to do with energy efficient cooling, which is becoming more important. So already neodymium iron boron magnets are used in the most efficient type of air conditioners today. They are also enabling a whole new type of solid-state magnetic refrigeration, which is emerging now. So there's still a lot of work going on in studying the materials and the devices in magnetic caloric refrigeration. And I should just point out the fact that here we don't have any toxic gases, so we're not contributing to global warming. And as well, the actual energy conversion is more efficient than in traditional gas phase cooling. And so while it's very much an active research field, there are already commercial magnetic caloric fridges available on the market. So just to say a little bit about some work we're doing in Grenoble. So if we think about length scales, or maybe more correctly, the weight. So in a hard disk drive, you're talking order of about a gram or a few grams, let's say. Here in the cars, it's a few kilos. In windmills, you're talking about a few tons, but as Richard Feynman said, there's plenty of room at the bottom. So we would like to actually try and get neodymium iron boron magnets into micro devices, so just small systems, and which can actually, they can be actuators, motors, whatever. And these are already being, now not magnetic, but other type of microsystems which are performing these, which have these types of devices are being used in a very wide range of different application areas already. And the big advantage with microsystems is you can get reduced cost per device. If you can reduce the magnet size, then you can reduce the size of the device, and this obviously has advantages in smartphones and IoT, Internet of Things devices. Another thing is you're going to use less of the rare earths. So this is just some very recent work where we succeed in making magnets which are of the same quality as the sintered magnets, but now we're working at the scale of a few microns, and we're using clean room facilities to do this. And so here we did, with colleagues from other labs in Grenoble, we developed an energy harvester. We're not going to save the world with our energy harvester. It's more just a sort of demonstration to show that it was possible to make excellent quality neodymium iron-boron magnets using the clean room facilities which are used to make MEMS. Now, I'm not going to catalogue, I'm not going to list all applications of neodymium iron-boron magnets. If anyone can read fast, they can see stuff here. But it's important to realise that there is growing demand for neodymium iron-boron magnets, and especially when it comes to the hybrid vehicles and wind energy. So this all sounds very encouraging, but then there's the big problem that we know that unless you've had your head stuck in the sand for the last few years or last 20 years, rare earths are critical and strategic elements. So already there was the rare earth crisis in just after 2011, 2012, and this was sparked by a political spate between China and Japan, and so the Chinese just stopped selling rare earths to Japan, and this was a big problem because Japan makes excellent high-performance magnets, so let's say the prices went back down, but they're on the rise again. But let's say the Chinese didn't want to sell the magnets to the Japanese, but now I'm afraid the Americans actually just want to steal the rare earths from around the world. But anyway, let's move on. But it's very important to realize that the criticality of rare earths. And so there is an article, a report that was written a few years ago about the significant, the strategic importance of rare earth magnets and motors. So if anyone's interested in more, they can look up this. Something I just want to draw your attention to is that China already has a big chunk of the market when it comes to mining, but then as you go across the value chain, they're getting a bigger and bigger fraction of the market. At the moment, Europe has a nice big chunk of the windmill market. But of course, if we can't buy the magnets, we can't make the windmills. So it's very, very important to address this whole issue of the criticality of the rare earths. So there's a lot of effort now going into investing across the full raw material value chain, and we'll hear just after about what we can maybe hope for from Sweden. But when it comes to, so I'm working in the field of permanent magnets, so there is already a lot of work has gone into recycling permanent magnets. There's a lot of work around substituting the most critical elements in the high-performance magnets that Dr. Sagawa developed. And there's also work going in to try and actually search for brand new materials, brand new hard magnetic materials. And just to say that these are two fields which can actually benefit a lot from current developments in high throughput experimental, but also artificial intelligence and computational methods. And there's work going on about that in Sweden and other countries in Europe. So just to say a few words about the idea of element substitution. So we know if we consider just the 214-1 phase that Dr. Sagawa discovered, if we look at today's applications at room temperature or low temperature, we're essentially using praseodymium and neodymium. If we go to higher temperature applications, even though, so Dr. Sagawa has shown that it's almost possible it's possible to suppress the need for heavy rare earths, but nevertheless they are still being used to make magnets used in some of the higher temperature applications. And so the whole problem here is that as you go across the lanthanide series, there's less and less of the materials. It's becoming a lot more. The materials are becoming a lot more expensive, and this is why it's really essential that we explore the use of cheaper. And so here there's a lot of work going on now to try and use lanthanum or cerium to partially substitute. I mean, you'll never make a good magnet with just lanthanum or cerium because the intrinsic properties of the phase are not sufficient. But we can hope to reduce dependence on even neodymium. So this is a very important step going forward. So if we want to make a new magnet, so first of all, we have to find we have to find a good phase. And so in the case of neodymium iron-boron, it was really the experience and intuition of Dr. Sagawa that identified this phase. Now we have tools using electronic structure calculations or machine learning to try and find other materials. This work can be supported by high throughput experimental studies, be it thin film or bulk studies. But with this, we can try and identify promising phases. Then we have to try and make it, and we have to characterize the intrinsic properties. So this all looks very good, but if you actually want to make a magnet, then you have to develop the appropriate microstructure. And this is extremely challenging. And what's so impressive with neodymium iron-boron is that Dr. Sagawa went from his discovering of the material right through to making magnets in a few years. And nobody has, in the intervening 40 years, no one has found a new material that can challenge this. So to conclude, so I hope I've convinced you that neodymium iron-boron are really critical for our daily lives. The materials now, thanks to the excellent work of Dr. Sagawa and other people working in it, they have almost reached their theoretical limit, at least in magnetic performance. I think it's unlikely, based on what we know today, it's unlikely that we're going to find a new permanent magnet that will be even better than neodymium iron-boron. There is some work going on recycling, but there's still a lot has to be done in this field. And as I mentioned, there is a lot of work which can also be done in improving the performance-to-cost ratio. So if we start substituting neodymium with lanthanum or cerium, okay, the performance is going to be, it won't be as good. It'll be a little less good, let's say, but it can be a lot cheaper, so we can improve the performance-to-cost ratio. And this is something which is being supported by high-throughput experiments combined with AI and computational methods. And if I have 30 seconds to show, just again, coming back to our work in Grenoble, we're using the thin film combinatorial approach to study the effect of substitution of cerium and lanthanum. So like we'll take a 4-inch wafer, we're going to sputter films, and we deliberately have a gradient in the content of the neodymium, cerium and lanthanum. And then we study the magnetic and structural properties as a function of composition. And the reason I want to show this is that an important characteristic, like we have to characterize these materials using X-ray diffraction. And if we characterize them using X-ray diffraction in the lab, it takes about a whole weekend. Here we have a bunch of these substrates. So this is a 4-inch wafer where we have a gradient in the neodymium iron cerium lanthanum. Now we're using this robot, which has neodymium iron-boron magnets, to position the sample here. Then we have neodymium iron-boron magnets, which are holding the sample in place. And even more critically, out of this hole, we will have this very high flux X-ray source, and we can use this to study the materials. And the synchrotrons work thanks to the, not neodymium because we have to cool them down, so we're going to replace it with praseodymium. It's a detail. But I just think it's nice to show that we are already trying to address the problem, but using the neodymium iron-boron magnets that got us here. So thank you very much.
Thank you so much. Fantastic, Nora. We now understand that we really can't live without them, can we?
No, I don't think so. I can't imagine a world without neodymium iron-boron.
From now on, I can't either. You know what? I would actually we have a few minutes now, so if any one of you have a question to Nora, and we will find time for that. But I would like you first to just elaborate a little bit more on the recycling business, and if there are other sort of business models we can use to. I've heard something about leasing magnets instead of owning them. Can you just give us some examples?
So just to say a few words now, I'm not working in recycling myself, but from listening to colleagues working in it. So if you want to recycle a magnet, you can have the short loop where you actually take the magnet. Well, the shortest loop is if you can just take the magnet out of a device and use it in another magnet without modifying it at all. That would be wonderful, but it's not very realistic. But you take a magnet, you can crush it into powder and resinter it. But the problem is you're taking magnets from all different sources, and I just talk about neodymium iron boron, but in truth there are maybe about 10 different elements, because there's always a little bit of something that's going to affect the microstructure, and which is critical for the actual extrinsic properties. So a big challenge with recycling when you're using the short route, where you break up the materials and you're mixing them to make new sintered magnets, it's the fact that you don't know what's coming in, okay?
I see. You can't really trust it, can you?
And so you're limiting a little bit what you can get, and also even when it comes to engineers who are designing systems, it's very important that you design your systems that it's already easy to get the magnets out. But even if you do get them out, you're mixing them. So let's say there's a lot of challenges, and in Europe there's been a big effort, a lot of money gone into developing recycling. But a couple of months ago, then China ban the export of the technologies, the presses that you're using to make these magnets. So it's like they're as if they're pulling the rug from under our feet. So there's a lot of work, which still a lot has to go into the whole recycling story. So it's far from resolved.
It's far more complicated than we thought.
And another thing is that if you consider the growing demand, even if we do manage to recycle the magnets, it's still not enough. So I think maybe a message to Sweden: you have rare earths, please, we need them.
We will talk more about that in a minute, but are there questions? Otherwise we continue with that perspective.
I have a question.
Do you have a question? Good. Can you use the microphone by your chair, please? There is a microphone just there. Thank you.
Is it?
Yes, it's on.
Yeah. So that was exactly my question. It's what I understand. I'm an electric machine design engineer, and so for me, it's not the mind that are the problem, but it's the science behind how to make these magnets.
Oh.
I don't understand why in Europe we cannot have our own scientific centers or scientists who can make these magnets. Is it patents, or it's we didn't invest enough, or how much time does it take to invest?
So it's all a question of let's say. There are loads of researchers working on making magnets, improving magnets. There's a few companies, not many in Europe, which are making permanent magnets, and it's simply because the Chinese can dominate the market because they have control over the rare earth value chain. So Japan is still a maker of very high-end neodymium iron boron magnets, but it comes down to the cost, and China is able to make the magnets cheaper. And therefore they can, so in the article, in the report that I just flashed up there, I can tell you more about it, give you more details. But there it really shows that it's not a level playing ground when it comes to the cost of getting the materials and then actually manufacturing them. Mm-hmm. And as I said, so recycling is only going to address a small fraction. If we want to be able to keep producing machines which use these magnets, we have to be able to secure the rare earths, because he who controls the rare earths controls the magnets. He who controls the magnets will eventually control who can make devices using them.
We will continue with these rare earths. So thank you so much for a question, and thank you so much, Nora Dempsey. Thank you so much. I would now like to invite another EVA fellow, adjunct Professor Magnus Eriksson. He has many years of experience in mineral economics, and he's the co-founder of AMG Consulting, a Stockholm-based firm that, if I'm right, provides insights to the global mining sector. I'm introducing you now, Magnus.
Thank you.
And what I really would like you to talk about, Magnus, is the connection now to Sweden and Europe, because, I mean, you mentioned cerium, for instance. Jöns Jakob Berzelius was the one who actually identified it for the first time. And we are so proud in Sweden because we have so many scientists that actually identified those those elements in the periodic table. But tell us a little bit more, Magnus, about our situation today and forward also. So please, you have 8 minutes. I know this will be a challenge for you, but
my time.
I'm sure you can do it.
Absolutely. I'm very happy that I'm trained as a biochemical engineer. I'm a professor of mineral economics, macroeconomics, and my colleagues claim that I am not a true professor. I'm just an amateur in economics. But this is a photo gives you my background. The lady in the middle there, she's my grandmother. This is a mine in central Sweden. They'd mine iron ore for perhaps 700 years or something. This photo is taken in 1910 when my grandfather took my grandmother to his home place. That's where he came from before they got married. And this is now, what is it, 1910, that's 110 years. I got started into the policy of minerals in 1970, so it's almost half that period that I've been engaged in this. I think it's interesting to look at this, that the mineral processing was done by hand by ladies. So the gender balance was much better in those days than it is today. I have 3 slides. I'm going to highlight 2 observations for both of them. Ytterby mine, I'm very happy that I will be the host of the Japanese delegation on Friday. I'm engaged in saving this mine for the future. It has been in danger of getting simply gentrified and houses being built there. But in 1785 or 94, sorry, the first rare earth was identified here. And what is interesting, that was not something that happened just by chance. Already in 1639, the first chemical laboratory was set up in Sweden to support the mining industry. So it took 150 years or something to get to something really a scientific breakthrough. And I think this is something to learn also for politicians today. Science and research has to be over the long term, perhaps not 150 years, we can wait these days, but nevertheless, these geologists, chemists, if you like, they were very ingenious when it came to the chemistry, but I must say, I think they were rather, they didn't have a lot of imagination when they named Ytterbium, which is the name of the village. By is village in Sweden. And they started with that, yttrium, terbium, erbium. 4 names of elements after just one little village. That's something where they could have performed better, I think. But the Swedish engagement or Swedish connections to rare earths didn't stop there. You might wonder, what is this? Well, this is a Swedish explorationist, Sven Hedin. He's world famous in all of Sweden. He actually had an expedition in China in 1927 when they first identified the Bayanobo iron ore deposit, which is later one of the most important deposits for rare earths. So there was a strong link here between Sweden and China. And, well, we have already heard a bit about China today and their dominance in this industry. But I'd like to go back a little and just make all of you aware of the fact that in 1975, 1980, China did not produce any rare earths at all. In that period from 1975 to 85, they came to dominate the market. So, well, perhaps Europe and the US shot ourselves in the foot, I'm not quite sure. But there was industry also in Finland, for example, rare earths were produced, etc. So this is a very complicated situation, how the Chinese managed take over this industry. But in the most recent days, there has been discussions about Greenland and Ukraine. President Trump says, well, I want to have all the rare earths coming out of these countries. My first observation is that, yes, there is a rare earth deposit in Greenland. Sarfartok is the name of this place. But it's impossible to produce in Greenland at a profit. The infrastructure isn't there. There are no people. And I've been very much engaged in Greenland. And it will be almost impossible, I would say. Ukraine, there is another problem. There are no rare earth deposits. Well, I think that it's important to note that geologically rare earths are no problem. Mining, not a problem. The problem is the low price. So we have to deal with that somehow, to be able to produce and control, get some control over the market. My final slide, 1, 2, 3 here, is the Swedish mining cluster. And I think this is also important to understand that Sweden, I showed you the mining history. Still today, Sweden is among the most important mining countries in Europe, second only to Ukraine, as a matter of fact. But what Sweden has, which no other mining country has in Europe, and perhaps not even the world, that is an extremely strong mining equipment sector. The Swedish manufacturers of equipment for underground mining has perhaps half the global market for this type of equipment. And then we have the third part, which is a dynamic exploration center and also very important R&D, research and innovation. So this together is the Swedish mining cluster. And I would say that when you take that mining cluster and at the same time you realize that in Sweden are the perhaps two most important deposits of rare earths. We have a deposit in southern Sweden called Norra Kärr, and we have the deposit which is co-located with the iron ore mines in the north. And if you take those deposits together with this mining cluster, I think that is it would be the absolute duty of Sweden and the Swedish mining cluster to start using that deposits and those possibilities, if for no other reasons, for simply military and political security reasons. So those were my 3 slides, my 6 observations, and I just like to end with a conclusion here. Madam Moderator, how am I doing?
You're just fine.
Thank you.
5 more seconds.
Yeah. So, as I said, I think that the Swedish mining cluster should be mobilized to secure the rare earths for Sweden, for Europe, and for the rest of the world. Thank you.
Thank you so much. Magnus, we had a question over there regarding the Europe situation. How could we sort of be in this industry together, collaborate in Europe? And also Nora talked about that. What strategies do you think we need to adopt in Sweden, but also in Europe, to sort of secure those critical raw materials? You said we could do more in Sweden, but how can we do that?
Well, the deposits are there, and but there are permitting processes which are difficult. And
what about the environmental situation?
Well, the environmental situation is, of course, part of the most important permitting part, and that can be solved. It's only a matter of production cost. So if there is a real political will to secure a rare earth industry in Europe, It is not difficult. It's not costly either, I would say, because as you know...
But you just said it came with a cost.
Yes.
So the cost is higher than actually importing them from China?
Yes, what I'm talking about, absolute amounts.
Okay.
You know, there's only 150,000, 200,000 tons of rare earth produced every year. Copper, for example, 20 million tons. And actually, so I don't think it's a major economic problem. It's a problem to have the political will to say, okay, we will have to take those costs.
Because the alternative might be, in the long run, even more expensive for us.
Exactly.
Thank you so much, Magnus.
Thank you.
Thank you. Now we will shift a little to another sort of aspect of magnetics, and this time we will actually dig into something that is so exciting, because this is one of the super emerging technologies nowadays. And it's called sometimes spintronics and so on, nanotechnology. We have today one of the leading scientists in the world in this topic here with us today. Professor Hideo Ono, he was the former president of Tohoku University, and he's an EVA fellow. You are globally renowned for spintronics and also nanotechnology. And your groundbreaking research is on spintronics particular, and now it comes. This you have to explain to us. The magnetic tunnel junctions, this is cool, and their applications in non-volatile memory. And this has greatly advanced energy-efficient information processing technologies. So with your understanding contributions, we understand that if we don't understand this after today, never. Please welcome Professor Hideo Ono. We are so excited.
Okay. Well,
please tell us more about the spintronics.
Okay. Thank you very much for the introduction. I'm an EVA fellow as well. And I'm also very proud that Professor Sagawa, Dr. Sagawa, is one of alumni of Tohoku University. So let me switch a gear a bit. And now I'm talking about magnetic materials and magnetism as well, but for information storage and processing. So spintronics is where you use magnetism. Magnetism is a collection of spins, and also a charge or current to manipulate magnetization. So that's spintronics, and that's good for green society. And we are hoping that it will contribute a lot to the world. And these are my collaborators, and as Eva told us, I will tell you a bit about magnetic tunnel junction. Tunneling is discovered many years ago in solid state, and that won a Nobel Prize in the 1970s. So the first part I will discuss about non-volatile memory and working memory, and the second part I will discuss about probabilistic computing, both using magnetic tunnel junction. So let me start with non-volatile memory part. So this is compute energy versus year, and this is the world's energy production, total energy production, which increases approximately 2% per year. And we all know that the data centers are consuming a huge amount of energy. So if we extrapolate what we are seeing today, it looks like this. So slightly beyond 2040, we will end up using all our producing energy to compute. And that will, of course, will not happen. But those people who compiled this report at the Semiconductor Research Corporation in the US, they predicted this green line. But that's also too much. And we need to do something about okay, let me see. We need to do something about increase So the reason why we have so much energy, there are many reasons of data center energy usage. The problem here is that they don't disclose it. But many people believe that 20 to 30% of the energy consumed in data centers are used by these working memories. And current working memories, they have two versions, dynamic random access memories and static random access memories. And those high bandwidth memories consist of dynamic random access memories. The problem here is that they are all volatile. Volatile meaning that you have to keep your power on in order to keep your information there. So basically, this is what you're doing. You turn all the rooms lights on to work in a building, even though you're not using many of the rooms. So actually, you want to do this. You want to turn off all the light of rooms that you're not using. But you cannot do this without non-volatile working memory. So that's the reason why we are working on non-volatile memories, non-volatile working memories. And here I compared NAND flash, which we use for our smartphones, and other type of working memories, non-volatile working memories. NAND flash is a wonderful memory because you can. It's extremely inexpensive. But look, this endurance part here. Oh, sorry. Endurance part. Sorry. Okay. Yeah. Endurance is very low. It's once you write 1,000 times, it breaks down. So it's not good for working memory. Here, I will not go into too much details about the slide here, but the good part of spintronics magnetic tunnel junction is that it operates at low voltage. Here on integrated circuits, the supply voltage is usually 1 volt, and you can use it within this voltage range. Okay, sorry. So this is a magnetic tunnel junction. It consists of two, as I promised, magnets, ferromagnets. One is strong magnet that it's not easily to change its magnetization, N-pole, S-pole direction. The other one is still stable, but with help of spin polarized current, we can change its direction from up or down by spin transfer torque. And it's separated by a very thin insulator, thin enough so that your electrons can go through. So the resistance between this parallel configuration and anti-parallel configurations are different. So that's why you can read the configurations by electrical means. And beyond a certain threshold current, depending on which direction you run current through the device, we can set the configuration in parallel or anti-parallel. So even though you only have two terminals, you can read the state and you can also write the state. So that's how this one works. And any non-volatile memory has an energy barrier between two states, in this case 1 and 0. This energy barrier has to be high enough so that it will not be disturbed by thermal fluctuation. Otherwise, you will accidentally have 1 changing to 0 or 0 changing into 1. Okay, so there are many stories behind this technology, but this is the latest one that made final sort of device. So all the technology or magnetic random access memory semiconductor manufacturers are basically using this configuration with cobalt ion boron, which is a ferromagnet, another cobalt ion boron with very thin MgO. And the crucial point here is that we have to make, I will not explain why here today, but magnetization perpendicular to the plane for the efficiency purposes. But people couldn't do it and struggling to get this one. And the beauty of this material set is that this is extremely common material, cobalt ion boron MgO, and all the labs are working on it, but they couldn't find this perpendicular anisotropy because the parameter space that you can get this perpendicular anisotropy was rather unusual, meaning that we had to make all the ferromagnetic material very thin. So we were fortunate enough to get this part with systematic studying. And although I showed very simplified version, the version that people are using, and as well as us, are very complex. These numbers are in nanometers, so on average, this is 0.3 nanometers over 300 millimeter wafers. So it's surprising that people can produce this very thin layer over 300 millimeter wafer and still can get a very good uniformity. So we use this technology to experiment, proof of concept, building proof of concept integrated circuits using Tohoku University's spintronics 300 millimeter line. I will not go into the detail, but basically the message here is that you can actually reduce the power consumption in some cases by 3 orders of magnitude and 2 orders of magnitude. So that's a great technology to reduce the power consumption of data center. And it's already in the market. You can buy those products that have these magnetic random access memory spintronic devices, which will last much longer than the Apple Watch that I have here. Okay, so one technology that you need to develop or show the world is that this technology is scalable. So meaning that we can go down to very small dimension without losing the properties. But this is a slightly complex diagram, but this is a device size, and this is a thickness. And red is good, E over kBT. Energy barrier is high enough. But as you reduce your device size, it comes down to yellow and then blue, which doesn't work as a non-volatile memory. So we had to overcome this problem or issue or challenge. And the way that we did it was to explore a wider region here. And the reason why we have a small dimension and very good stability here is simply because we are making a bar magnet. Bar magnet magnetizes in its actual direction, and so if we make these devices small but long, we can get a very stable magnetization in memory. Took us 3 years to get this shape, but it's working now. So again, it's shape anisotropy. Here, this is a standard line here. You're reducing the energy barrier here, but with a shape anisotropy, with the help of shape anisotropy, we can go up to 80 or more E over kBT, which is good enough for any applications. So we are now down to 3 or less than 3 nanometers, which means that we can go along with shrinkage of semiconductor device dimension. Okay, I'll skip this part. So that's how we have developed non-volatile working memory. And the second part of my talk is about probabilistic computing. Using exactly the same device, magnetic tunnel junction, we can make them very unstable. Let's say, so I discussed about this diagram here. And if we go on and use, let's say, thicker ferromagnet, we also reduce energy barrier in a controlled way. And once we get to a rather small energy barrier, we can observe this telegraph-like dynamics. Here, these are not typo, this is second. So within 10 milliseconds, we can see up and down or changing magnetization directions of these magnetic tunnel junction. So, and it can be controlled by running current through it. The proportion of 1 or 0 can be changed. So using this, we can build a probabilistic computer. Back in 1981, Richard Feynman at MIT gave a very famous talk in which he introduced quantum computing. You know, if you want to make a simulation of nature, you'd better make it quantum mechanical. But in the same talk, he also mentioned that the other way to simulate a probabilistic nature is by a computer which itself is probabilistic, and he suggested about probabilistic computing. So we can construct a probabilistic computer. In this case, although there's equations and diagrams, but basically this is an optimization of this equation here, which allows us to do integer factorization. So this is a number that you give them the computer, and these x, y are your answer. So when your answer is there, the energy is 0. But when you're off, then energy will become larger. So by looking at the probability of appearance of appearance of those stochastic or probabilistic magnetic tunnel junction, we can solve this energy by solving this in an optimization problem. I will not go into the details, but these are algorithms we've taken from adiabatic quantum computing. Okay, so this is the result. Initially, they are all random. We're using 4, 6, and 8 p-bits. P-bit is a combination of our stochastic unstable magnetic tunnel junction with transistor. And by going through the proper feedback, we can get 35, we can factorize 35 into 7 by 5 or 5 by 7, 945 to 63 times 15, and so on and so forth. You know, the lowest energy part will give you the highest probability of appearance. So this is how we solve a problem. And the good thing is that they are all asynchronous, so we don't need any clock to operate those p-bits, which means that we can get millions of them, and we don't have to worry about clocking them. And we can also simulate a class of quantum circuits by those magnetic tunnel junctions. All right. So we did a proof of concept of spin-tronic speed computer. I just mentioned about combinatorial optimization. We can also implement machine learning. We can also do quantum simulations using small number of p-bits. And the good news is that there are industries making those magnetic random access memories that I have mentioned earlier, with 1 megabit or 1 gigabit of magnetic tunnel junctions. So you can get an infinite number of, almost infinite number of those p bits. And so if we million of nanosecond, well, I should say nanosecond, that was millisecond version, but we succeeded recently to show that the flip, we can make it extremely fast magnetic tunnel junction, unstable magnetic tunnel junctions to nanosecond. And as I said, you can have 1 million or even 100 or 1,000 times a million on a chip. So if 1 million of those magnetic tunnel junctions are integrated, this is power consumption versus sampling throughput measured in flips per nanosecond. We predict that we can go here with less energy, higher throughputs. Compared to this NVIDIA's GPUs, N1 to N4, G1, G2 are Google TPUs. And the reason why they're having this, we're comparing this, is because generative AIs are using those probability to predict the next word. And it's natural. They're also multiplying huge matrices, but also they're working on a probabilistic approach to optimize and to identify which word comes next. And for these reasons, I believe that we can get a good hardware for next generation generative AIs and also machine learning, things like that. So this is my last slide. What I've told you today is that we can make magnetic tunnel junctions stable enough to make your data center low power. And we on the other hand, on the other extreme, we can make those magnetic tunnel junctions extremely unstable, which we can utilize to do something useful as well. So thank you very much.
Thank you so much. This is truly sort of brain, what do you say, damaging almost. Okay. Because when it comes to probabilistic things, you know, you can't really understand it, can you?
Well,
you get used to it, I suppose, and you can do the maths.
Yes.
But you can't really see it in front of you.
But we're using it.
I know. That is why I think it's so strong. I would like to invite also another EVA fellow. Please give a warm hand to Johan Åkerman. Because, yes, you are also a physicist working in this area, but you will soon tell us a little bit more about what you're doing, because that is like a second development of this. But I would like to also, for all of us, to know that you are a professor at Gothenburg University. You're also a fellow at KTH, or guest professor. And
he's also a professor at Tohoku University.
I know. I was just going to say that. So I see this connection. And I know that you are in Japan quite a lot. And you have a strong interest, Johan, both for the basic science in this and the applications. So first of all, what we have seen now, is it basic science or is it applications in your mind?
No, that's what's so great. It's both, of course. So the most fundamental material science, it goes into making these cutting-edge magnets, the neodymium iron boron and all the other rare earth elements that go into them. And then you can immediately, you know, we completely rely on that fundamental science to rapidly get new
and it's so
industries booming.
This shift, you know, from basic science to applications. What would you like to say about that development, Hideo?
Well, we no longer have a long incubation time from science to, well, it depends on field, of course, but some subjects you immediately can get an application. So we have to be aware of that the situation is very very different from, let's say, 20, 30 years ago. So we have to be ready, look at the basic sciences and how to combine those basic sciences to applications. It's very quick these days.
It's very quickly. It wasn't like that when Richard Feynman was a professor at MIT.
Richard Feynman was...
but he was always ahead of his time.
Yes.
I'm amazed. He's mentioned twice this seminar. And speaking about that, I would like to know, if you combine now what you touched a little upon it, about AI and the generative AI. If we combine this spintronics, the next sort of generation here, we can understand that you're talking about, with AI, what happens to us humans here? Are we completely off because we are so slow? And what will happen? Do you see any risks in this at all? Or are you just fascinated? You can stop.
Well, any technology has certain risks. So if we misuse them, we will have to suffer from the risk. But at the same time, this technology will allow, hopefully, us to have a generative AI in your smartphone, only for you, so that this knows what you would like to do and what your preferences are, and it will answer the questions that you ask. So it will become more personal.
More personal and more fast, I suppose.
Fast and energy efficient, of course. Otherwise, you will not be able to put it into a smartphone. Whether this is a good feature or not depends on how we use them.
But since this development is so fast now, we really need to get more knowledge into this field, I think. So what do you say about combining those emerging technologies? Is that something that gives you headache, or?
No, for now it's just exciting. That it's a very strong and powerful tool to become more creative as a human being, I think. So far, it doesn't look like the creative spark is there in AI, although I'm not an expert of that, but it certainly is a fantastic tool to enhance or augment your own creativity, to get more done, because you can fill in the blanks. You know, let's say the creative mind is opening up a new direction, a new space, and then you can use AI to fill in that new space. But maybe reaching for that new space is probably still human, but I don't know if it's going to be that long.
Perhaps that's another seminar,
also done by AI.
We need to have another seminar on this one. But you know what, Johan? I would also like you to talk in your words about this probability computing, and you called it even natural computing, and I thought it was so fascinating that you sort of shifted there, that either the computer itself is sort of probabilistic or the world, or how we can combine this. So
yes,
please, can you try to explain it once more for us?
Well, you're letting the physics do the computing. You're letting nature do the computing. These bits are just randomly flipping, and then you let them interact with each other.
But it's a truly, sorry, I'm interrupting. It's a truly unstable system.
Yeah, the bits are random. They're true random,
and still you can trust
number generators, and then you make things with them. So instead of having completely stable voltages, you have fluctuating voltages, and then you're going to let those voltages add up. And you're going to get an average result, but depending on how you add them up, how do you add them up, how you lay out the circuit with these random number generators, that will now do the computation. And no longer you have to keep that voltage there. You can just let the system fluctuate. Exactly. And you save energy that way. And you also explore a parameter space that way in computational terms.
Because you can let it work in parallel, as I understand it. Yes. You can actually.
Yes.
So it's so much efficient.
Yes. And Johan is working on quantum version as well. So,
can you tell us more about that?
So we're doing a third thing of using the magnetic tunnel junction. So the memory is the very stable one, the probabilistic bit is the unstable one. And if you use an intrinsic resonance in the magnetic tunnel junction, it's called a ferromagnetic resonance, you can drive that flipping, you can drive it at a pure frequency. So a pure microwave frequency, let's say a few gigahertz, 5, 10, 50 gigahertz. And now if you make those oscillators very small, we can make them 10 nanometers big, and you can place them very close to each other. They start to interact. So now you can build oscillatory networks, oscillator networks, and they too can do things in parallel. So they too compute through their interactions. You're not telling them, do this operation, do this operation. Instead, you're telling them you're going to interact with your neighbors with this strength and this phase. And then you let them figure out where their ground state is.
It seems to be quite a lot like the brain works?
Yeah, I would say so. There are similarities.
So in that case, it's also more natural, would you say?
So it's again, you're not telling this system what to do. You're telling the system how to interact. And then the system finds a solution to the same kind of problems that quantum computers try to solve. So a whole class of combinatorial optimization.
But this is not quantum computing.
No, it's classical, but it's parallel.
Exactly. And it's what is it that we have heard you speak about? Because I would like to tell my friends tomorrow, I listened to Jan Åkerman, and he is an expert in...
Well, icing machines.
Icing machines, okay. That didn't
is what
make
we call them. But,
okay, you call them icing machines because...
Because they are driven or they're governed by an equation that a German student, Ernst Ising, was given as a problem, figure out how magnets interact. And out of that came the Ising model. And now I'm a little sloppy, so I say the icing machine, but the Ising machine. So that's the historical part of it. But he didn't figure out the machine. He did this 100 years ago for the model.
But both of you, is this what we've talked about just now? Is this the next generation? This is not even electronics. This is spintronics. This is next generation. How should we even... We don't even have the language to talk about this yet.
Well, people are already using, probabilistic approach, even in digital computers. That's one of the reasons why they had to spend so much energy in GPUs. But we are trying to figure out that let the physics entities do the job.
Let the physics do the job.
And they will perform much faster and less energy.
So with technology, we have sort of come so far now that we can actually move together with basic physics.
Yes.
To solve problems that we are into because we have not found this yet. We are sort of lost. How would you like to explain the time we're in and the next generation technologies?
Well, that's a big question, but it's very exciting that we can augment what we're doing, what we're already doing. We can augment that with deep neural networks or other forms of AI and machine learning, because in the collaboration between, you can have physics-inspired AI. You can have which then with that you can part of your system that you don't understand, you let an AI figure out. So you let an AI or a deep neural network figure that out. Part of the system that you understand completely, you have equations for, and then that together becomes a very powerful combination. You can also do this in optimization. All kinds of optimizations can be used with both AI and the combinatorial techniques that Professor Ono and I are working on. You can use icing machines for one part of it, and then you can use AI or deep neural network to operate on the icing machine.
So you have another instrument now to actually understand things. Do we have any questions, or is this perfectly clear now for all of you? Admit that it's exciting, isn't it? And remember where you heard it first. Maybe you are all into this area, so you just think, oh, they talk about it. I know this already. I think we've learned a lot today, and I'm so glad that both of you, you also, Johan, came and discussed this with us. Thank you so much, Professor Hideo.
Oh, thank you very much indeed.
Fantastic to have you here. And now I would like to hand over the stage to Mr. Ambassador and for the closing remark. And the Ambassador of Japan to Sweden, your name is Mitsukoshi Hideaki. Give him a warm hand. And thank you both.
Good evening, distinguished professors and guests. My name is Hideaki Mitsukoshi, Japanese ambassador to Sweden. As a co-organizer of the top scientist lecture, I would like to say just a few words as a closing remark. Sweden and Japan have both special places in the world of science, technology, and innovation. There are active collaborative research between universities in Sweden and Japan, and those exchanges are producing creative results. At the government level, the importance of academic exchange between the two countries has been repeatedly confirmed. Most recently, science and technology was one of the important pillars in the joint statement of strategic partnership, which was agreed last December when Prime Minister Ulf Kristersson and Prime Minister Shigeru Ishiba met in Tokyo. This top scientist lecture, which was originally developed in 2014 by the EVA and the JSPS in order to introduce prominent Japanese researchers to Sweden, is just a wonderful example of such an cooperation. So thank you very much for all the speakers and the moderator. I won't say I have understood all, but honestly speaking, yeah, I wouldn't be honest if I said I understood all, but still, I learned a lot. Through today's lectures about magnets for sustainable world, so I learned how new materials such as neodymium magnets have been developed, and they are playing very important role for the EVs, cell phones, therefore for digitization and green technologies, which are also a very important agenda for Japan-Sweden cooperation. So I think these academic exchanges can develop into a more industrial cooperation. And also, as I heard that there is a strategic importance for products using rare earth, I think it can be a very strategic cooperation between the governments as well. On another note, recently, a Japanese airline, ANA, has launched a direct flight between Tokyo and Stockholm. I believe it will promote not only tourism, but also academic exchanges and business cooperation. I suppose some of the participants here have come here with a direct flight with the ANA. I hope that this direct flight will provide a very comfortable journey for the future Nobel laureates from Japan. Also, let me mention that Japan is hosting the World Expo 2025 Osaka, Kansai this year. So people's interest toward the expo is very strong in Sweden, and there will be a big Swedish delegation in May to Osaka. And some of the universities have announced their participation in the expo at the Nordic Pavilion. And I am hoping it will also be a good trigger to enhance our academic and scientific exchanges between Japan and Sweden. So, tack så mycket.
Thank you. Thank you again, fantastic speakers. I'm actually honored to give you a little sign of our gratitude, and it's a book on Swedish innovation. So, thank you so much. It's especially nice for me. Thank you so much. Thank you so much. Thank you so much. Thank you. Nora. Thank you so much. Thank you, everyone. Thank you so much.